Good morning and thank you for joining us. I'm Emily Velasco, a content and media strategist with Caltech's Office of Strategic Communications. It's my pleasure to welcome you to Conversations on Sustainability. This series is hosted by the Caltech Science Exchange and gives us a chance to hear from scientists and engineers who are working on the cutting edge of research and technology that can mitigate the effects of climate change and help us build a more sustainable future. I'm joined today by Stephen Lowe, the Frank J. Gahlon Professor of Computing and Mathematical Sciences and Electrical Engineering. Hi, Stephen. And Adam Wehrman, Professor of Computing and Mathematical Sciences and Director of Information Science and Technology. Together, they're working toward developing a smarter electrical grid that will allow us to make better use of sustainable energy sources. Dr. Wehrman, Dr. Lowe, thanks for being here.
A pleasure.
Okay, so let's get started. I have a number of questions today, and we're gonna go through some questions, and then we'll get to audience questions after we go through these. My first question is, I think for people watching at home who maybe aren't totally familiar with the topic, we hear a lot of talk about the grid these days, but what is the grid? I feel like if you ask most people what it is, they might point to the power lines they see outside, but there's a lot more to it, right? Like, in layman's terms, what is the grid?
Yes, indeed. So the grid tops the National Academy's list of the greatest engineering achievements in the last century. It is a gigantic infrastructure that transfers energy from where it is generated to where it needs to be. So besides the hundreds of thousands of power lines that we might see, it also contains about tens of thousands of large generators, and also about the order of billion of loads. So these are the buildings, these are computers, these machines and lightings and so on. So the main challenge is that we have to balance supply and demand at all times, at all points of the grid. And hidden in this infrastructure is a very complex web of control mechanisms that help balance. But also integral to the control mechanism is also a very elaborate market structure that brings together suppliers and users to incentivize socially optimal resource allocations, but also have to mitigate market power manipulations. And one of the biggest challenges going forward is how do we transform both the control mechanism, but also the market structure to support 100% clean electricity. And that is very difficult. So the grid is mostly transparent to users, as it should be when it works well. And it is most noticeable when there are control or market failures. So traditionally, these kind of failures have been relatively rare, but can be catastrophic. Going forward in the future, they can be both frequent and catastrophic unless we overcome some of those challenges. And these are some of the issues we've been working on at Caltech.
And by market, you mean the literal buying and selling of electricity. Producers sell electricity to people that consume electricity, right?
Yeah, I mean, one of the surprising things to a lot of people is that, yeah, it's not just wires, it's, both the engineering that governs the control and, and that sort of, fine-grained, physical infrastructure, but also this economic infrastructure that ensures that you have generation when you need it. I mean, it's amazing to think that you are able to balance load, the usage and the generation at every instant, at every time, in every location, always. And if you fail to do that, you have power outages. How do we not have power outages all the time? It really is an amazing achievement, not just an engineering achievement, an economic achievement, that this stuff works every day for us.
And so on that topic, that you said what it does well. Like, we don't notice most of the time that we have a grid because almost any time you can turn on a light switch and have your light come on. But what does the grid not do well? And what kind of improvements does it need?
Yeah, I think the reliability is really what it does well. It's amazing, but what we're facing today as we try to make the grid more sustainable is, basically the integration of things like wind and solar is a direct attack on the reliability of the grid. So the standard operation is to plan ahead, to predict what the demand is going to be everywhere, turn on generation to make sure, turn on and off generation to make sure that you do have this supply and demand balance at all points of times and all locations. And that works because you can predict pretty accurately. And so you don't have to worry too much about, correcting. You don't have to correct an enormous amount. But with wind and solar, prediction is hard. I mean, these are unreliable, variable, uncontrollable resources that are sustainable, which is great, but that create just enormous challenges. And if you try to operate the grid going forward the way it has been in the past, you keep backup generation, conventional, non-renewable backup generation around on just in case. And if you do that to an enormous extent to counter the big fluctuations that can come when a cloud goes over or when the wind bursts or stops, then you lose the benefits for sustainability that you're hoping to achieve from wind and solar. And so, you really need new techniques, new market structures, new control policies, new everything to be able to use these renewable energy resources to actually make the grid more sustainable rather than to just shift basically counter that sustainability with backup generation that's not renewable.
Yeah, just to add to what Adam said, the grid was really designed where the control is almost entirely on the bulk generators. Like Adam said, we don't really control the loads very actively, but we predict. Now in the future, imagine those bulk generators, those are the fossil fuel generators, will be replaced by large wind farms and solar farms and also distributed like PVs on people's rooftops. Then we lose the control, the ability to control precisely when the uncertainty increases, that we need much more active control. And therefore, one thing that on the control side is a huge challenge is that now we control hundreds of millions of loads. So this is not done in the current grid. You need to have much more nimble and much more simple algorithms that are implemented not at the few control centers on the grid, but also in many, many devices, smart buildings and EV chargers and so on throughout the grid. And therefore, the distributed nature is one key control challenges. The second thing is that as uncertainty increases, as Adam said, that we really need to close the loop. So the real-time aspect is also not done well today.
Okay, so I think that takes me into my next question, which is, what is a smart grid? In our last episode of this conversation series, Harry Atwater, who was talking about photovoltaics, mentioned the smart grid, and he described it kind of like the internet, but for power or electricity. Is that an apt analogy?
It's a start of analogy. I mean, it's evocative of the right thing. I mean, in the same way the internet is a really complex network that delivers something. It delivers power, not data packets like the internet. There's some parallels, but actually the smart grid is a much more challenging and ambitious task than the internet in terms of managing it. And this is because of interaction with physical laws, Kirchhoff's laws for managing power flow. You can't, there's not a parallel to that in the internet. In the internet, you can really control everything as you want. You don't have to sort of face these underlying constraints that create challenges for your operation. And it's truly cyber physical in the sense that you're controlling devices. It's not just the wires, it's also the devices at the endpoints of the wires that you're managing, which is something that isn't the same sort of degree of challenge in the internet. And then the interplay that we've highlighted around economics and engineering, you don't just have a pure system that you can write a protocol for and separate and have a nice hourglass architecture that separates the bottom from the top. You have economic market design in that architecture of the grid. You have physical laws in that architecture of the grid that can't be abstracted away. And so there's a lot of things that make it in some sense much more challenging to manage. But at the end of the day, the goal is somewhat similar in that you want to enable communication and global operation of large-scale distributed resources in the same way the internet does that for our communication.
And so I guess where the analogy holds up is that right now our electrical grid is kind of like unidirectional. You send power out and it goes where it needs to go, but there's not that feedback. And I guess that's where it works. Yeah. Because it's closed loop, so you can get the feedback from your loads and adjust accordingly, right?
That's right. And in some sense, integrating the internet, or at least communication of that style, into the grid is one of the big parts of moving from, you know, the old grid to the more modern grid, and having that two-way communication, two-way control. And so, you know, there's a lot of techniques, and that's, you know, in some sense, Stephen and I both began in internet, and we're working on communication networks. And part of the reason to shift over was that there's a lot of similarities in the goals and the style, that you feel like that expertise can make a difference as you move into smart grid and energy systems broadly.
One example is the internet is much more distributed in terms of control mechanism. Yeah.
Now, Stephen, you've done some research that relates to this, and that is that you developed a smart charging system for electric cars here on the Caltech campus. Can you tell us a little bit about that project? Like, how does it work, and how does what you did with that research apply to the efforts to make the grid smarter and more sustainable?
Sure. Let me start by just motivating why EV is so important. So electricity generation and transportation, they generate almost 60% of greenhouse gases in the US, according to EPA. And therefore, to drastically reduce greenhouse gases, we have to electrify transportation and then generate electricity from renewable clean sources. Now, this is both a big challenge, but also an opportunity. It's a big challenge because EV consumes a lot of electricity and at extremely high power, at extremely high rate. So every single EV has about 1/3 of average household electricity demand, and much more in terms of the power demand. And therefore, if we electrify transportation, that's going to add a lot of stress. But EV is also an extremely valuable resource because it's extremely flexible. And this flexibility is going to help us integrate uncertain and volatile renewable sources, generations. And therefore, it's clear that we have to really encourage large-scale EV charging. Now, if we look at how that is done today, typically, everyone can plug in EV anytime, and you'll be charged at the peak rate. If you have 5 or 10 chargers in the garage, that works well. If you have hundreds or even thousands of chargers in the garage, like in LAX airport, then that cannot be done efficiently or economically. And therefore, if you think about, at least in the urban cities, the most valuable resource in this whole ecosystem, charging ecosystem, is actually the real estate. And therefore, in the future, what we want is that every parking spot comes with a EV charger. And in that scenario, you cannot charge the way we do, but it's also unnecessary. So if we look at Caltech, for example, once we build the test bed, typically EVs stay for on average 6 hours, and they finish charging in 2 hours. And therefore, the right thing to do.
Sorry, if I can interrupt for just a moment. Just to be clear for people who don't know, EV means electric vehicle, just in case people didn't know what we were referring to. So I'm sorry for interrupting. Go ahead.
Thanks, Emily. That's right. So, and therefore, the right thing to do is not to charge every single EV when they first plug in, but you use algorithms and software to optimally schedule the EV charging process, so that you need the minimal infrastructure in terms of electricity distribution, but still every driver will get the energy demands. Say, I need 30 miles today before their deadline. And this is really the key for large-scale EV charging. And that's what we've done starting at Caltech. And then eventually we transfer the technology to the marketplace.
Okay, so I'm sorry, if I understand correctly, so like, let's say everyone shows up at the office at 9 a.m. to start their workday, and everyone plugs their electric vehicle in at the same time. Like, that's too much of a load for the system to handle, to charge every car at the same time. And so what you've done is develop a system that says, like, you know, this is what time you're coming in, this is what time you're expecting to leave, and your car needs this much charge. So like, this car is going to get charged now because that person is going to leave earlier today. This car is going to get charged later. And that way the cars are taking turns instead of trying to all charge at the same time. Is that right?
Exactly. So when the drivers plug in, indeed, we just ask them those two questions: when do you expect to leave? How many miles do you need? And then with that information, you can optimally schedule the charging process. Okay.
And Adam, were you going to say something?
I was just going to say, yeah. So, and I think, you know, this is just to emphasize, you know, I think the importance of what Stephen's been able to accomplish here. So within a garage, the bottleneck is really the line coming in and how much power that can hold, right? So if you can spread that out and charge 50 cars instead of 5 cars, you reduce a huge barrier to EV adoption. But also you give a huge knob to the grid more broadly to use for incorporating renewable energy, because once you have this adaptability of charging in every spot in a garage or multiple garages around the city, now you can give feedback signals from the grid saying, we're stressed right now, there's a lot of usage, we just can't afford much, can you dial back? Oh, we have a lot of solar right now, we can take a lot more charge, please do bulk charging right now. And so you can become kind of a virtual storage device for the grid. You can make use of these cars in that way while still respecting the deadlines and constraints and the goals that the owners of the cars have for their charging. And that sort of opportunity is enormous in terms of enabling the smart grid, enabling integration of renewables.
Yeah. So one thing to add to what Adam just said about the using the solar. So for those who, some of them you might know about the duck curve. So we are generating in California from times that more solar than we can consume. So this is called the duck curve problem. There's a valley of net demand to the grid. Now, if you look at today's duck curve, if you want to fill the valley, you can charge 13 million EVs if you do it at the workplace. Now, as a reference, California's goal is to have 5 million EV by 2030. And California has about 15 million. And therefore, the duck curve that we are seeing today and certainly going to have in the future will be sufficient to really charge the EVs that we need, as long as we do them smartly.
So I guess I have 2 questions based on that. One is are there lessons in adaptability that you can apply to other sorts of loads on the system besides EVs? And that's to say, people use electricity in their homes and we use electricity in factories. Is this idea of adapting our loads something that would be more widely applied than just charging vehicles? And then the second part of this question is how does something like that, and you got into it a little bit with the duck curve, how does that adaptability allow us to make better use of sustainable energy sources?
Yeah, I think, the answer to the first question is definitely, a lot of the work we do at Caltech is about finding this adaptability in important large-scale users of electricity. And so one example is EVs. A lot of my work has also been around data centers and computing and adapting the usage of compute to be more carbon-free or carbon-aware. And so, to highlight the importance of that, training an AI model, one of these big language learning models that, companies do, that training process has been estimated to kind of have the same carbon footprint as the lifetime emissions from 5 cars. And so, but at the same time, that kind of training process is not time sensitive. It's not something where you need it instantaneously as quickly as possible. Often it's something that can be done flexibly and adaptively. And so again, if you can have systems in place that help that training process be, integrated into the grid in a way that, it lets you know when there's renewable energy available, lets you know when is a bad time to do it, when is a good time to do it, then you can start to fill in these valleys where, you have a lot of renewables available, but you don't have a lot of demand, and you can avoid the places where there's a lot of demand and not much renewable available for that kind of computation. And so smart buildings, data centers, EVs, all of these give opportunities for this kind of exploitation of flexibility on the demand side, the consumer side.
Yeah, one thing we're seeing already in the industry indeed is to look at the joint optimization of the solar generation, the EVs and batteries and buildings, the controllable loads jointly.
Okay. So my next question is, what is the timeline for the development of a grid like you guys imagine? It probably happens in steps. There's probably not a clear line at which a grid goes from a dumb grid to a smart grid, but what is the kind of timeline we're looking at for development of a grid that can make good use of sustainable energy sources?
Right, so there are 2 aspects. One is that what kind of timelines do we actually need? And then where we are with the gap, can we realistically achieve that? So we look at the timelines that we need. If we want to stay on the pathway to, let's say, 1.5C above the pre-industrial level of emission, then it means that we have to reduce emission by about 80% by 2030. So that's extremely ambitious. If we say we want to stay to 2 degrees Celsius above the pre-industrial level, that timeline is about mid-century. And that's why a lot of the states like California, for example, have committed to have 100% electricity generation, clean electricity generation by 2045. New York is 2040. So there are more than a dozen states that have already committed to 100% clean energy or electricity around the mid-century. So that was one timeline. So where are we? So we still generate about 60% of our electricity from fossil fuels. So that's better, already about 8% or so, much better than, let's say, a decade ago. But still, we have a long way to go. Now, electricity generation, again, is so important because if we have to electrify transportation, and then we have to generate electricity from clean sources. And that's why this electricity generation or the grid transformation is so important.
Yeah, and maybe to follow up a little bit. So, I mean, in some sense, a lot of the infrastructure has reached a place where it can be, integrated and implemented already. So there's smart devices for sensing and communication that are being deployed. Solar and wind are cost competitive. So a lot of that means that there will be progress in the short term. And the question is kind of when different regions across the world or across the US hit this wall where you kind of need something new, where the current architecture stops being enough, where you start to see reliability issues hitting because of the integration of unreliable wind and solar. And so when that kind of reliability wall hits is when power outages start to kind of become more likely, when costs start to go up because you have to have lots of backup generation to counter the random fluctuations. All of these issues start to come into play. And kind of our research and a lot of the research in the community is targeted on kind of getting through that wall, breaking down that wall so that when you get there, you can still progress. Because I think, a lot of the short-term progress is, we have the devices, we have the infrastructure to be able to make it. The question is when we need an architectural change, a control and economic change to be able to keep progressing. And I think that's kind of about, maybe one way to frame the smart grid is it's kind of the thing that enables a partnership between kind of the demand, the users and the grid. It's always been one way. The grid just is the service that gives you what you need. And at some point, it's going to have to be more of a partnership. There's going to be communication two-way back and forth and control. And that partnership is where the smarts and the smart grid comes in terms of enabling it. And that's where our research is about, is focused.
Are there any countries that are leading the way on this? Like, is there anyone out there that's a good example of building a smart grid or a more sustainable grid?
There are certainly a lot of activities on around the world on this energy transformation, energy system transformation. So there are a few countries that are really lucky, and they are the majority of the country that we really need to work hard. So in terms of the number one, using low carbon technology to generate energy, Iceland actually topped the list. They generate 79% of all its energy from low carbon sources. And for Iceland, it's just hydro and geothermal. And Norway is also very lucky. They generate more than 90% of the electricity from hydro. But most countries are not that lucky. So there are a lot of activities around the world. So Germany has a lot of wind, UK has a lot of wind, China has a huge investment in both solar and wind. Another interesting case is Australia, which is a small country, but they have the largest batteries energy storage that is in operation, commercial operation. So there are many experiences that we can learn from, the challenges that we see around the world when they get to a certain level.
For reference, you mentioned Iceland having 79% of its electricity from low carbon sources. How does that compare to, like, say, the United States, or how does it compare to average?
So the world average in terms of low carbon generation of energy, not just electricity, is actually very low. It's about slightly less, slightly higher than 16%, around 16%. US is around that in terms of all energy, not electricity. The good news, though, is that among the low carbon technologies, renewables already exist hydro and nuclear. So that is a really good trend in the last, say, 15, 20 years, but we still have a long way to go.
Yeah.
Yeah, and I think, emphasizing that, right, there's countries that start at different places because, if you have a lot of hydro or geothermal, these are not just low carbon, they actually are easier they make managing renewables easier because of the way they can provide sort of storage-like qualities for the grid. And so, we aren't as lucky in the US to have a huge penetration of those. California has, a lot of some, the Northwest has a lot of, these as well, but nothing like in Iceland. And that means that we're hitting our wall, or we're likely to hit our wall earlier in terms of the need for architectural change. But every country is you're seeing the progress slow as you get to that point where you need this architectural change, where you need different markets and different control to be able to overcome the hump.
Okay, and when you say that things like hydro and geothermal are in a sense kind of like storage, what do you mean is that like they're predictable? Like the ground is gonna, you can predict that the ground is probably going to stay hot, so you're going to get power there. Your river is probably going to flow, unlike solar where it might be cloudy one day and you just don't have electricity. Okay.
That's right.
They're controllable, and that's extremely important. So geothermal is steady. Hydro is controllable.
Yeah.
Okay.
Yeah.
Both are very good.
Okay. So my last question is, the grid, the smart grid is going to be very different than what we have now. It's going to be a very different system. It's going to be perhaps more complicated, but is it going to feel different to the average person in the audience today? Is the average person going to notice a change in a significant way if they go to flip on a light switch or charge their car?
Yeah, this is a really good question, because it's in some sense, one vision for the smart grid is that you should have all this smarts there to provide the operation and all of this, but it should still remain simple for the homeowners. And this is a strength and a weakness in the sense that, if it still is remaining simple, where is all the smarts? But at the same time, there will be things that happen for the average homeowner, I think. Hopefully we get to a situation where, the air conditioning, fridge, these sorts of appliances can pre-cool based on availability of renewable and signals they get from the grid, where you have energy storage devices that can provide backup if there's an outage and can charge, when it's sunny and discharge when it's not overnight. You have an EV that charges smartly, like Stephen described, and maybe actually is also a backup generation for your home in case of an outage. So there will be, I think, improvements that the homeowner sees, but to a large extent, I think the big difference, the big benefit is sustainability. So the smart grid will enable sustainability, which will let us get to these 50, 70, 90, 100% targets. And if we can do that, then our whole society is more sustainable. Our air is cleaner. We've mitigated climate change to some extent, hopefully, as we go forward. This is really crucial for all of that. And on the other side, if we aren't successful in enabling these changes, then we're going to have major challenges to our grid in terms of increased unreliability, increased failures, and homeowners will experience those things directly. So in some sense, smart grid is hopefully about avoiding the bad. There will be some niceties that come from having smarter infrastructure around our homes and our buildings, but we're trying to maintain and enable that transition to sustainable infrastructure.
Right. So one little detail I latched onto, this is a little bit of a sidetrack, but you mentioned EVs being used as a generator or a backup generator for a home. Like real quick, can we say what that is? Because I hadn't heard about that before.
Yeah, I think, the hope would be that, the EV is a large battery sitting outside your house. And so, if your power goes out and you still need your fridge, if it's hooked up in the right way and the controllers are smart enough, you can use your EV to power your fridge for a little while, which is really great if you have things in there. I remember a number of stories when I had young babies where we were really trying to save the milk for the baby, and power outage were very, very stressful, right, to make sure that those things didn't go bad.
This is a tremendous resource because we drive probably less than 2 hours every day on average, and therefore it's a really good resource sitting there that we should certainly exploit.
Yeah, because it's a big battery and it's just hanging out in your garage most of the time, right? Okay. All right. Well, we're just about out of time for our questions, but are you guys ready for some audience questions? It looks like we've got quite a few. So
Definitely.
Okay, great. All right, so let's see. All right, the first one I see, this is kind of interesting question. And this is kind of relates to the internet aspect of it. The question is, it seems like a smart grid would have more security vulnerabilities than the current grid. Can you address how that needs to be handled? I guess the idea is if you're having two-way communication, then there's more places where malicious actors could get into the grid.
Yeah, I think this is a great point. It's a crucial thing. I mean, this requires security, whenever you have this kind of communication. It does, potentially open vulnerabilities if it's not done well. And so there's a huge research focus and industry focus on trying to enable security for this. At the same time, it also gives you, it's a double-edged sword because it also gives you increased ability to respond. So, one of the big challenges in sort of historically for the grid is failures, whether they're nefarious or not, have the potential to cascade. And so, one issue in one place of the grid could spread. And because of the physical properties, it doesn't just spread locally. It can create a failure 20 miles away, 30 miles away in a seemingly unrelated part of the grid. And those can be really dangerous and hard to control. And the smart infrastructure hopefully can provide localization, islanding abilities to respond in smarter ways as well. So I think it opens the door, and that needs to be dealt with very carefully and with really rigorous separation, and making sure that systems don't interact in ways that access or hacking in one aspect can impact another, but also it lets you respond more proactively because of the communication and infrastructure.
Yeah, so one thing we learned from internet is that the security really needs to be designed when we start to think about transformation of the smart grid. It has to be built in. And one of the things we also explore is the fact that we have a physical system. Now, of course, it makes some aspect of the security more challenging, but also it also offers additional features that we can use to really counter the cyber security aspect.
Yeah, and I think an important point here that many people in the area realize is this is not a situation where you take internet security and you layer it onto the grid and all of a sudden you're secure. That's not a valid approach. It will not solve the problems. It will introduce more problems than it solves. It has to be something built in a different way, taking advantage of the fact that this is a cyber physical system, not just a cyber system.
This is an important lesson, right? Because if I understand correctly, security wasn't really a consideration when the internet was built. And so it hasn't been built like at its most bare bones level with security in mind. And so we've had to layer security on top of it. But if we're building the grid now, the smart grid, you can build the security into the grid, right?
That's right. And it's crucial.
Okay. And I guess kind of related to this question is like, this is another question, is who would be the keepers or the safekeepers of all of this? Like, how do you manage all that security when you have so many utilities and interconnected grids?
So this is a tough question. I think both because security is a tough aspect, but also because it's the smart grid from the architecture, both the control and market architectures are still being sorted out. And therefore, it's not very clear how that should be done. Now, there are a few features that I think that are clear. One is that currently the grid is mostly controlled by a few control centers that really control the bulk generators that determine, say, the dynamics and also stability properties of the grid. But that will no longer be sufficient. There will be a lot more active nodes that will be controlled actively, and also by different organizations that may not share information, that may be in competition with each other. And therefore, the security architecture that people are actively working on must take that into account. So it will permeate through the physical infrastructure, but also you need the coordination among different parties, whether it is the generators or the control centers, whether it's the utility companies, or even community control mechanisms that control several distributed resources in the community.
Maybe this is a good question to sort of highlight that it's important to think of security for the smart grid, not just in terms of security, cybersecurity type things. There's also market security, right? Because markets are used to control the actual infrastructure. An attack doesn't necessarily have to be, you know, a hack on a device that then sends a bad signal or whatever. It can be an attack on a market structure, and you know that can market failure can have just as dire an impact as we saw in Texas. And so, you know, having these sorts of market designs that are robust to fluctuations, either nefarious or not, is, you know, as you know, is also important in terms of ensuring the security of the grid.
So we have a few like kind of related questions coming in that sort of are around the topic of like bridging the gap between when you have supply being generated and demand being needed. So like one question is, if everyone needs to charge their EV at night, but solar is generated during the day, like how do you get the electricity that was created during the day to people at night? Another one is like, how do you provide backup if there's like a heat wave, but you don't have enough supply for everyone to run their air conditioners? Like how do we make that connection between the two?
So a couple of points to make. Again, this is a challenging problem. So the easy part of it is that the workplace charging really needs to be exploited at scale, because because of the duck curve issue, more and more solars, there's a lot of opportunities that we can charge EVs and even just batteries for where you need outside, let's say at night. So that's the part that is significant but relatively easy to be done. Now, if you worry about if you have prolonged, let's say, insufficient sunlight or wind for days, that is a much more difficult situation. Now, there's several things that needs to be done. One is that large scale, longer term storage technologies, they are such technologies. They all have limitations today. Scientists are working very actively on that issue. Can we have large scale, inexpensive, long-term storage? So the storage is one aspect. The second aspect is certainly the demand. There's a lot of potential in reducing the demand at times of need. So last year, August 2020, that there was a rolling blackout through California because we need to reduce electricity by 2 gigawatt hours. So 1 gigawatt hour for 2 hours. And after the mayors and governors that called on California to conserve, you save 4 gigawatt, and there was no longer a rolling blackout. So this is just an emergency mechanism, but it indicates the potential for reducing the demand in times of need.
Sure, and that's a good point, because if you ask people to conserve electricity, there's not a way to tell them exactly how much to conserve, right? But that's where the smart grid comes in. And if I remember correctly from the news, maybe earlier this year, there was some news out of Texas where some customers of a utility had agreed to, I think it was, they would get a lower electricity rate if they gave the utility the ability to control their smart thermostat. So the utility could say like, hey, we're under a lot of load right now, so we're gonna raise your home temperature by a few degrees. And I think that there was a lot of people complaining at the time, but is that something we're gonna see more of, where we can more precisely, like from a central hub, tune how much electricity like is being used by the grid?
Yeah, I mean that's kind of the first version, the alpha version of these sorts of programs is, give up control, trust us, we'll manage your electricity, we won't use it too much, and you'll get some money back. So that's one version of programs. There's a variety of programs being studied and proposed that are of that flavor, that are slightly more sophisticated than the send out a mass email, please help us and use less energy, that can be a little bit more targeted. And the hope is that that kind of thing can become increasingly present, and that actually this ends up being something where if you're flexible, you're getting paid for it. You're getting cheaper electricity bills because you're willing to be flexible in how you use, and because that kind of ability to be flexible is valuable to the grid. And actually, I mean, this taking this point broader, I think there's a to make concrete the idea of why we need our organized markets, and it ties into this for electricity, because if you think about it, as we have more and more wind and solar, the marginal cost of electricity is dropping. And so if we get to 80–90% penetration, the marginal cost of energy is basically zero. And that means that how are these generators going to make money? What is the service they're providing? How do they stay in business? And it's somehow a shift where instead of paying for power or energy, you're paying for reliability. You're paying for a guarantee that it will be there when you need it, rather than the marginal, paying the marginal cost, which is the traditional way markets are designed. And that shift from the good, the thing that you're buying being energy or power, to the good being reliability, is kind of the crucial shift in market architecture that has to happen over the next 10 years.
We have another question about EVs, and this relates, we talked a little bit about how you could, in theory, use your EV as a backup power source for your home in a blackout, but someone asks, has there been any thought given to, say, using all those EVs that will be plugged into the system, using them as a source of power, like using them to balance grid? So if you need to pull power out of the EVs to balance things, is that something that's possible, and is that something that's being considered?
Oh, absolutely. So this is very much an active topic in research. Now, commercially, there are pilots and startups trying to do this, what's called V2G, vehicle to grid, to do exactly what you said. And this is actually absolutely something that we should exploit. So just to illustrate the potential, for example, so last August, we had rolling blackout for 2 days. If we assume the future EVs, they just reserve, say, 20% of their battery capacity for this kind of emergency use, you only need 200,000 EVs to have avoided last year's rolling blackout in California. How many EVs do we have now? In the US, it's about 1.8 million, and about half of them are in California. So we have a lot of EVs that can provide a lot of potential services.
Yeah, I mean, a very concrete version of that vision is, think of all the cars parked at LAX at any given point. Those people are not going to be using their cars for a day or two or a week. Imagine if all of those were plugged in and those batteries were being used in a vehicle to grid way to manage and help balance fluctuations of the grid. All you need to do is ensure that when the driver gets back, they have, the energy they need in their car's all full. But, in the meantime, that car could be making money for the owner by, providing this balancing service. So instead of paying for parking, you come back and, there's a check that you receive for the service that your car provided to the grid.
Looks like we've probably got time for maybe 1 or 2 more questions. This one's kind of interesting. Someone wants to know about the phenomenon of microgrids. I've heard of microgrids, and I assume that just means a smaller grid, but can we talk a little bit, like, what is a microgrid and how might these microgrids play a role in building a smart grid?
Right, so there's a few aspects that are important in the transformation of our energy system that microgrids can play. One is that it is so for example, Caltech is a microgrid. So we generate about 80% of our electricity on campus. And a microgrid is simply a system where you can have generations in addition to loads that you can control. So typically a microgrid is connected still to the macro grid, but more and more of them will be designed and operated so that they can actually operate in what's called the islanding mode when it is disconnected to the grid. Now, what's good about this clearly is reliability. If there's any issue with the macro grid, then you can still self-sustain. The second important thing is that you can actually generate within a microgrid, and if you generate assets, you can actually potentially trade with other microgrids in a P2P manner. And that also helps the balancing for the entire grid as well. So yes, and the challenge is that the 2 important challenges. One is the market aspect. If you have lots of these microgrids that is connected to the main grid, but if they only take advantage of the main grid, so who's going to pay for the fixed infrastructure in the main grid? So the market, the economic aspect needs to be sorted out. The second thing is the control, where if the microgrids turn on and off because of whatever is beneficial to the grid themselves, then again, how do you maintain the stability of the overall grid?
We've got like 1 minute left. I'm going to ask, this is sort of I don't know what this question is asking exactly. I don't even know if this is a real thing, but someone asks, can quantum electricity generation be a reality? Is there quantum electricity generation? Is that a thing?
Quantum electricity, not clear.
Okay, well, we'll just skip that one. Well, we've got just a little bit less than a minute, so I think we can call it on this one, guys. This was great.
Yeah, this was a lot of fun.
Yeah, thank you for joining us. If you're interested in more of these conversations, our next event in the Conversations on Sustainability series is coming up next month on November 12th, when my colleague Whitney Clavin will talk to JT Rager, an earth scientist at the Jet Propulsion Laboratory, which Caltech manages for NASA, and Indrani Graysick, a program manager at the NASA Western Water Application Office. And they're going to be talking about how NASA monitors water resources from space using satellites to help us respond to drought and make more sustainable water management decisions. In the meantime, if you're interested in exploring more science-driven solutions for a warming planet, please check out the Caltech Science Exchange. The site provides trustworthy answers and clear explanations on critical topics in science and technology. You can find it at scienceexchange.caltech.edu. And thank you for joining us.